Hello, everybody. Today, I'd like to talk about energy and collisions, as you see here. I'm going to start off by talking about what energy is and then explain how it applies to the context of momentum transfer we talked about last lesson. Now, I want to start off by talking about what energy actually means. And there are lots of definitions out there, and one pretty rough one is that energy is the capacity, and please write this down, is the capacity to perform an action. Or I should just say actions. Right? The more energy you have, the more actions you can do. Think of it in the context of a car, for example. You want to drive further, you need more fuel. And what is fuel? Fuel is energy, right? It's not a very physicsy definition. It's a pretty, like a layman's term definition for what energy is. In physics, or I guess in nature, energy manifests itself in different ways. You might have heard of terms like kinetic energy or gravitational potential energy or strain potential energy or whatnot. There are many, many different ways that energy manifests itself. And the first one I want to introduce for us today is energy that we call work. We call work. I'll just switch colors here. Work. Okay. Now, this term work doesn't mean like job, like a job, like when you work for a company. Work here is given to describe a type of energy or a type of way that we use energy. So when we say work, we typically mean the energy used to displace an object. That means to move it from location A to location B. So if an object went from here, from location A to location B, we have to give it a sprinkling of energy, right, into the system to move it from location A to location B. Now, there is a formula for work, and I'm going to write it down now. So work equals to Fs cosine theta. Okay, now F is force in newtons. S is displacement, not speed. It is displacement. Much like in SUVAT, we label it by S. And cosine theta is the angle between the two, right? Well, the cosine of the angle between the two vectors, right? And these are two vectors. So, for example, a really, really, really simple, and the final units of this, the final units of work, I should mention, is Newton meters, and we abbreviate that sometimes as joules, very, very often as joules. So joules here is the unit of energy, and well, that's basically it. So let's have a look at a really simple, scenario. We have a block here, and I'm exerting 20 newtons of force, and it covers a distance of, say, I don't know, 15 meters. Let's assume this is 20.0 for the sig fig people waiting. Let's have a look. So the work done to displace this object from position A to position B is just going to be the force 20 times 15 times cosine of the angle between these two vectors. So the displacement vector is this way, and the force vector is that way. So they're parallel. So the angle there is 0 degrees, right? So cosine of 0 degrees. Cosine of 0 is just 1, so it's just going to be 20 times 15. Okay, and that's whatever that is, 300. Okay, 300 joules. Oops, let me just zoom back in. 300 joules. If the force vector or the displacement vector was at a different angle, of course, we'd put that angle into that position. That's basically about it. A common example of when the angle does matter. So for example, let's say I don't know, there's a person on a travelator. Those things would just travel. They're like escalators, but they just go across the ground. There's a travelator and it's moving this way. There's a person and they're in the airport and they're really happy about their luggage, so they hold it above their head like that. So they're exerting an upwards force, a lift force there. And let's pretend, just for the sake of argument, it's 50 newtons. right? This person moves from A to B, and they move a distance of, let's say, 100 meters. Well, what's the work done? Well, let's think about it for a second. These two vectors, one's pointing this way. That's the lift force there, and the displacement vector is pointing to the right. So they're at 90 degrees. So the work done would be 50 times 100, that's Fs, times cosine of 90 degrees. Now that's 0. So the work done here is 0. And that should kind of make sense because this person here isn't using their energy to move from A to B. They're using their energy, I suppose, to keep the bag lifted above their head. But to actually displace them from A to B, they're not using any energy. So the work done by them is 0. The work done by them is 0. So there's an example of why the angle matters. Of course, if you had a different scenario again, where something was dragged at an angle theta here across some distance s, right? It's pretty obvious why we have to, why this isn't 0 either, because some part of the force indeed is pointing in the same direction. In fact, the cosine of that force is pointing in the same direction as the displacement vector, which is why we have cosine there. But I'm digressing. So here is, let me try and input a new page. Insert, wait, close that. Insert page, please. Blank page. Sweet. Okay, let me introduce you now to a different type of energy, and that is kinetic energy. And kinetic energy is one of my favorites. Right? Kinetic energy. And from the name, kinetic means movement, right? Or moving. So this is the energy of something moving. Okay. So the formula for kinetic energy, and this is the symbol that I give it, EK, energy kinetic. Sometimes you might see it as capital KE. Okay, it's in places. This is my little abbreviation. Is 1/2 times the mass of an object times its velocity squared. Okay, that is the formula for kinetic energy. So when something is moving at some velocity, that's its kinetic energy. And that's going to be really important for today's class on collisions, because we can look at how the kinetic energy changes. There are also other forms of energy, and I'll list them all. Gravitational potential energy. That is mgh, or what I often write as delta h, so a change in height. But we'll get to that a little bit later. The one that I want us to really pay attention to is kinetic energy. EK equals 1/2 mv squared. Now, coincidentally, the kinetic energy, and this is another formula you should write down, the work done equals to your change in kinetic energy. Now, I can derive it for you and prove it for you, and I'll do that very quickly, maybe in a future class, actually. Maybe not for today's class. I'll do it in a future class. But to explain why this kind of makes sense, why the work done equals to the change in kinetic energy, if you think about it, let's have a look at this scenario here. If an object is under the action of a force, it means it's accelerating. And if it's accelerating, it means its velocity is increasing. And if its velocity is increasing, that means its kinetic energy will increase as well, right? Because kinetic energy is dependent on velocity squared. So if there's some work done to displace an object, it means a force has been applied, and therefore acceleration has been applied, velocity is changing, kinetic energy is changing. So the work done should equal to a change in kinetic energy. There is a mathematical proof which says that they're directly equivalent, they're directly equal, but I'll show you that at a different time. The one thing I want to introduce before we continue is the fact that energy, the total energy of a system, that means it's kinetic plus its potential energy plus any other weird energies like electrical or spring potential energy. The total energy of a system, it's always constant. It never changes. Now, you would have learned this hopefully in year 10, that the total energy of a system is constant and that energy can always be transformed from one form to another. It can never be created or destroyed unless you're like a deity. And if you're a deity in my year 11 IB physics class, you should definitely be doing other things with your time. No, this fact of nature is that that energy cannot be created, cannot be destroyed. It can only be transformed from one form to another. And a really easy example of that is when, for example, I'm talking about kinetic energy here. Let's say, for example, you drop a basketball of some kind, right? And it hits the ground. Well, it'll bounce back up, then it'll bounce back down again. It'll eventually settle to the floor here, right? Well, what happened to all the kinetic energy of it falling? Well, it turned into sound, right? It turned into the kinetic energy of air. It even turned into heat. The ground underneath it, the molecules there are wobbling a little bit more. In fact, if you like slapped the table or something and then looked at it through an infrared camera, you would see the tables heat up a little bit. So the energy of the ball certainly is dropped, yes, but the ball isn't the only thing in the system. There's also the ground and the air, and the energy is just converted from one form to another. Okay. Now, when it comes to collisions, we specifically are going to look at kinetic energy only. We're not going to look at anything else. We can analyze how the kinetic energy of an object changes when it collides with something else. So let's have a look at this really simple setup. We have a 10 kilogram object. Let's say it's traveling at 1.0 meters per second. And then it collides with a 5 kilogram object, which is initially stationary. After they collide, I'm trying to zoom out here. There we go. Thanks, Microsoft Word. There you go. After they collide, they stick together or they meld together in some way, some weird way. And then they travel off together. In fact, let me just make it extra obvious. There's the 10 kg object here and the 5 kg object there. So it's kind of pushing it along, so to speak. They're together. Well, I can ask a couple of questions. The first one is going to be, what is the velocity of this object? And the second question is, well, what's the kinetic energy of like before the collision? And what's the kinetic energy after the collision? Has that changed? Has that changed, or is that constant? And your initial guess may be, well, of course it's constant. You said energy is constant. No. Total energy is constant. Kinetic energy is one part of that total. Kinetic energy can change. I'm not saying it has, but it can, right? So what we're going to do is we're going to find the final velocity, and then we're going to find the kinetic energy before and after the collision. And we'll talk about it once we get there. So the velocity after the collision, I invite you to pause the video here. Hit that like. No, I'm just joking. Please don't do that. Actually, no, hit the like button. That's a good thing. You don't have to subscribe though. I only post like once a year. It's probably not worth it. What was I saying? Okay, yeah. So find the final velocity of the 15 mass object. So the way we do it, much like you would have seen in last class, even though I haven't taught last class where I am now in the time frame. Whatever. I'm digressing. Let's have a look. See, I need to scroll down a little. Maybe zoom out a little. That might be better. Okay. So the initial momentum is going to be 10 times 1 plus 5 times 0, which is 10. That's nice. The final momentum also has to be 10. Now that equals to mv of the system after the collision. So that equals to 15 times the velocity. Yeah. So that means that the velocity equals to 10 over 15. And that's whatever that is, right? 2 over 3, 2/3. Okay. And 2/3 is, what is that, 0.6. So how many sig figs do I want? Yeah, I'll do 0.67 meters per second. Okay, that's the velocity of the object there. Let's now find the kinetic energy before and after the collision. Okay, so let's keep this handy. I'm now going to replace the little question mark there with v equals to 0.67. So we've answered the first question. That's fine. Let's get rid of all this. Okay. Hope you're having a good time. This is fun. All right. Kinetic energy before. So EKB, right? Energy kinetic before equals to 1/2 times the mass of the first object, 10, times its velocity, 1 squared. Don't forget the squared. Plus 1/2 times 5 times 0 squared. So I found the kinetic energy of one object, kinetic energy of the other. Added them together. Okay. You don't have to take direction into account here. Velocity is a scalar. It's not a vector. So it doesn't matter if this was moving left or right. You wouldn't put a negative here. Even if you did, it would be -1 squared. So it gets, the negativeness gets erased, right? So this is a scalar quantity. Doesn't matter. So when you actually calculate this, you'll find you have 5 joules of kinetic energy. If we then find the kinetic energy after, it is 1/2 times the total mass, 15, times 0.67 squared. And if I put that into my cellular device, let's see, 0.67 times 0.67, I get to 2 sig figs, roughly 3.4 joules. Okay, have a look at that. Okay, we have somehow lost 1.6 joules in this collision. Have we violated some fundamental law of the universe? No. When things collide, what happens? The material deforms, sound comes out, and sometimes even light does in collisions. All that indicates that energy, or kinetic energy, has been lost. Now, we classify this in a very special way, and this is something you should write down. I'll put it in green. If the kinetic energy after is less than the kinetic energy before, we call the collision, actually, I shouldn't even write less than, if it's not equal to, we call the collision inelastic. And that's not got to do with rubber bands or anything, it's just what we call it. We call the collision inelastic. And that can take 2 forms. In the case that EKA is less than EKB, like the one we have now, it's a kind of sticky collision, right? We have an object that hits another one, they stick together, right? That's what's happened here. That's what happens here. And so in that case, we say we have a quote-unquote sticky collision. And that's not a technical term, just one which I'm prescribing to it. But there's also another circumstance where the kinetic energy after is greater than the kinetic energy before. Well, when does that happen? Well, it happens with explosives. That's called an explosive collision. And it doesn't make sense to think about an explosive collision when things are breaking apart. But hopefully it makes sense, right? If I insert a new page, I'll draw it for you and show you why. In an explosive collision, you might have, for example, let's say this poor basketball again, but it's loaded with explosives. Currently, its velocity is 0, right? Its velocity is 0. So its kinetic energy beforehand is 1/2 times, let's say the mass is under 1 kg, 1 times 0 squared. It's just 0. But then it explodes, right? Then it becomes, a fragment of a ball that way and a fragment of a ball this way, right? This has, I don't know, let's say this is half the mass coincidentally, and this has half the mass here coincidentally, and this has a velocity of 15 meters per second. This is a velocity of 45 meters per second. So the kinetic energy after is going to be 1/2 times 0.5 times 45 squared. That's for the left bit. And 1/2 times 0.5 times 15 squared for the right bit. And clearly this is way, way, way greater than 0. So the kinetic energy has increased. This is an explosion. There is one circumstance where the kinetic energy is the same. If the kinetic energy before is equal to the kinetic energy after, we call the collision elastic. And there are very, very few places in the universe where you have elastic collisions. In fact, the only thing I can really think of which is truly elastic is like particle collisions. And even they are not always elastic. There's some weird, strange, otherworldly magician effects at those scales. But there you go. Today we've talked about collisions. We talked about work and energy. And then we've introduced the concept of kinetic energy into the fray. In doing so, we've actually defined something called an inelastic collision and an elastic collision. And we've talked about where that kinetic energy can go or where it has come from. In the case of a sticky collision, energy is lost to deformation of material, sound, sometimes light. In an explosive collision, the kinetic energy is come from what would have been the chemical potential energy within the explosive itself. There is one case, of course, where the kinetic energies are equal before and after the collision, and we call them elastic. You can get pretty complicated questions with that stipulation. For example, I invite you to try and solve the following question. we have an object here with a, let's say, mass of 1 kg, with a velocity of I don't know, let's do 2.0 meters per second, and it collides with a 4 kilogram object, which is initially stationary. And I'm going to specify that it's elastic. With that information alone, what is the let's say this is object 1, this is object 2. Actually, let's call it A and B. That'll be better. With that information alone, what is the velocity of object B after the collision? This is about as complicated a question we'll get, and I highly doubt you'll get this kind of question, often. But it's entirely possible it may pop up. So with this stipulation alone that it's elastic, what is the velocity after the collision of object B? And you would have to use momentum and energy to solve this problem. But anyways, I'm digressing. I hope that covered the information well. Now I'll leave you some questions for you to do. Thank you very much.